Alrighty, folks, welcome to the first lesson of Physics 20. Exciting stuff. So in these video lessons, I'm going to be going through the notes, same ones you've been provided in the Google Classroom. With physics, okay, it is very much a contact sport, meaning that you'll want to be following along, taking your own notes on pencil and paper. Okay, your brain is going to absorb the information much more effectively that way, and you're just not going to get as much out of a lesson if you're kind of sitting back and watching. So I strongly recommend printing out these notes if you are able to, and then you can actually follow along and fill in right where I am as you go. Okay, but if that's going to be tough for you to get them printed, you can also just use loose leaf. But I do ask that you are actually taking notes, actively engaging in each lesson, and not just sitting back and watching the video, but following along yourself, right? Then you can also do things like, make note of, for example, okay, this one I wasn't sure about. I need to book a meeting with Mr. Maxwell, right? You can take little notes and have a record of that for when it's time to review later. But all right, without further ado, here we go. Chapter 1, Lesson 1, Physics 20. We're getting going. Exciting. So we're going to start out here with just actually a review of some basic concepts from Science 10 and even previous science courses. Maybe not the most, exciting stuff on Earth, but it is super important. It's one of those foundational skills and pieces of knowledge you're expected to have heading into Physics 20. And so that is significant digits. That's where we're going to start anyway. So a review of significant digits. What is a significant digit? What's not a significant digit? And what are the rules around significant digits anyway? Okay, so all digits 1 to 9 are considered significant. They matter. Okay, so for example, if it's a number that's not a 0, we don't even have to think about it, right? Like this one, we've got a 287,326, 287,326. This has, count with me, 1, 2, 3, 4, 5, 6 significant digits. None of those are zeros, so we don't even have to think about it. They are significant. This has 6 sig digs. Okay. 34.2. Okay, decimal doesn't count as a digit, so we've got 1, 2, 3 significant digits, the 3, 4, and the 2. Okay, here is actually the only type of digit that is not considered significant, a leading 0. Okay, so we have a 0.01. Leading zeros are the ones that are leading the number. They're at the front of the number. Okay, so these two zeros are actually not considered significant digits. So we have not significant, not significant, significant. Only one significant digit. So one significant digit, it's that 1 there. Okay, same thing here. All right, ready? Stop me when I get to my first significant digit. Aha, the 3, right? So we have one significant digit. After that comes a 5. That is also significant. So we have 2 significant digits there. Trailing zeros, right? Contrast that to leading zeros. Trailing zeros are at the end. These are considered significant. We'll talk about this more in a second, but significance has to do with the precision those numbers are telling us about, right? So the fact that they're coming after that 1 gives us some information. They're telling us, okay, it's not just, 1 and then we're not sure what comes next. It really is 0.0100. So those zeros are significant. These two are leading zeros. They are not significant. So insignificant, insignificant. 1 is a significant digit, and then all these trailing zeros are also significant. So we have 1, 2, 3 sig digs. Here, right, we've got a 5 right off the bat. That's significant. And then these 3 trailing zeros are also significant. So that's 1, 2, 3, 4 sig digs. Okay. 360. Well, the 3 is significant, the 6 and the trailing 0, so 3 significant digits. 3.0, right? That gives us 2 significant digits. And again, you can start to see the idea behind sig digs here. They're all about the precision of our answer. So 3.0 is more precise than just 3, right? You're saying it really is, no, 3.0. It's not maybe 3.1 or we're not sure what comes next. We're saying it's right on the dot, 3.0. So it has 2 significant digits. Zeros between non-zero digits are also significant. So 103, 103, that 0 is significant. It comes after a 1, right? It's not a leading 0, so that has 3 sig digs. 103. 3001, significant. All of those zeros are significant. So 1, 2, 3, 4, 5, 6 significant digits. So to sum up, right, basically anything that is not a leading zero is considered a significant digit, right? That's the only one that doesn't count as a significant digit. So now that we've kind of reminded ourselves of what is and what is not a significant digit, right? Why do we care? Like what are the rules surrounding significant digits? Well, recall from previous courses, right? It's all about recording your answer to the appropriate level of precision, right? So the rules for the SIGDIGs that your final answer should have is that you're going to look at all of the data, all of the numbers that you used in your calculation when performing a calculation for a question, okay? Out of all of those numbers that you used, you want the one with the least number of significant digits. That's going to tell you how many significant digits your answer should have. So whatever the number of SIGDIGs, that number with the least number of SIGDIGs that was used in the calculation, that's how many significant digits your answer must have, okay? So at the end, when you've done all your calculations, you'll get your answer. You want to record it to that number of significant digits. You might have to round it off. You might have to add zeros, but that's the idea. Okay, now, important note right away here. You're not rounding at every step, right? Eventually in Physics 20, you'll get to the point where a question might take like multiple steps, right? In order to actually solve, you might have to calculate many things along the way. You never want to round along the way, right? For example, if you're just converting units, you want to use as many digits as you can to keep things accurate. I usually say 4 to 5 digits after the decimal is safe, right? This significant digit stuff, it's just when recording your final answer. And the reason for that is that if you're doing multiple step calculations, right, you're calculating lots of different numbers and then using those numbers again in the next step and then using them in the next step, well, if you're rounding them every single time, you can actually end up changing your final answer by a little bit because you've over-rounded, okay? So that's a common student mistake, is to remember the SIGDIG rules, but then think it applies to every single time they calculate a number. You just want to round to significant digits at the end when you're reporting that final answer. Okay, along the way, you want to keep some extra digits to make sure you're not over rounding and changing your final answer. So what is the big deal here? Why do we stress significant digit rules so much? I know it's sometimes presented as just, it's a rule, you gotta follow it, okay? It is important, you can lose marks for not following significant digit rules, but it's not just some made up thing that we did to trick you, right? It does matter. And the reason has to do with scientific communication, right? Being responsible in how we communicate that. Because we can only be as sure of our answer as we are of the values that we use to calculate our answer, right? It really is. It's scientifically irresponsible to claim a greater degree of precision than what was actually available to us, what we actually would have been able to measure. So to hopefully kind of convince you that, these aren't just magic rules, there is a logic behind them, okay? Let's just look at an example here. So suppose you were going to do a lab where you were going to measure the distance that a toy car travels with a measuring tape marked in millimeters, and you were going to also measure the time it took to travel that distance with a stopwatch marked in tenths of a second. And so you do the experiment, you do take your measurements, and your measuring tape tells you that it went 800 millimeters, because that's the lowest amount marked on your measuring tape, and it took 4.1 seconds to do that, right? Because again, your stopwatch only marks to tenths of a second. So this is what your stopwatch tells you. This is what your measuring tape shows you. Now, it would be irresponsible. Like, you can't actually say with confidence that it traveled 800.0 millimeters, right? You can't add a fourth SIGDIG there. You can't say that it took 4.10 seconds to do that. You can't add a third SIGDIG to that number, right? And the reason is because, well, you don't know that it was actually 4.10 seconds because your measuring device did not allow for that level of precision, right? Your stopwatch is going to say 4.1 seconds, but it could have been, 4.09 or 4.11 seconds. Your stopwatch only goes down to that tenths place. So you don't actually know what's going on over here after that last digit that showed up, right? So either way, if it had been 4.09 or 4.11 seconds, your measuring device would have returned the same result of 4.1. That's the precision that your measuring device offers there, right? So you really have no way of knowing. And this is what leads to our rules for how many sig digs our answer can have as well. Because now if we were to take that distance and that time and use it to calculate the speed of the toy car, right? Using this formula you know from Science 10, V, the speed is equal to the distance traveled divided by the time it took, right? Well, the precision of our answer for the speed is still going to be limited by the precision of those values, right? It still needs to be expressed to the same number of significant digits, no more and no less, because we can't suddenly claim to know the speed to a higher precision than the distance and the time that went into calculating it. So if we actually put those numbers into our calculator, we do 800 millimeters as the distance divided by 2.1 seconds as the time, here's what you're going to get. Here's what your calculator is going to show you. 195.12195.122. Our units there would be millimeters per second, right? Millimeters per second. We would maybe convert that to standard units depending on what we need for the question, okay? But look at this. This is what your calculator tells you, right? This is an incredibly precise measurement. This is way beyond what we were actually ever capable of measuring, right? We're talking now like down to like nanometers of precision. We do not know the speed to that high of an accuracy, right? We don't. We only knew the distance to 3 significant digits, and we only knew the time to 2 significant digits. So in fact, in order to actually write this to the appropriate number of significant digits, following our rule here, right, we are supposed to look at all the data we used, all the numbers we used, and our final answer should only have as many significant digits as the number we used with the least number of sig digs. So this only has 2 significant digits, this has 3, so 2 is the lesser of those, so our answer would need to be recorded to 2 significant digits. To do any more would be irresponsible. We'd be claiming a higher degree of precision for our speed than we were actually capable of getting from the data we had. Now, in order to actually do that for this, right, we're going to need scientific notation. So maybe I'll come back to that one after we've done a quick review of scientific notation, okay? But that's the idea here. Let's take a look at an example. If you were asked to solve the problem below, how many significant digits should your answer have? Okay, well, let's take a look at the question. A car is traveling 100 kilometers per hour on a highway for 2.2 hours. What is the distance traveled by the car in this time? So we would actually use that same formula, but we're not even being asked to solve this. We're just asked about how many sig digs should our answer have. Well, how many sig digs does this have? We're going to use that speed. It has 3 significant digits, right? Trailing zeros are significant, so 1, 2, 3. And then our time only has 2 significant digits, right? 2 significant digits. So if we were to do the math, calculate this out, figure out the distance, how should we report our final answer? Well, 2 is the least number of significant digits in the data that we used, so our answer should have 2 significant digits. Okay, so as we saw in this one, right, sometimes we're going to need scientific notation in order to actually use the appropriate number of sig digs. So scientific notation is a notation that allows us to A, always use the correct number of sig digs, and B, more conveniently express very large or very small numbers, which comes up more in physics 30 when you're dealing with, you know, tiny numbers and huge numbers, but sometimes in physics 20 as well, we will see tiny numbers and huge numbers that are a lot more conveniently expressed with scientific notation. So here's how scientific notation actually works, okay? You're always going to have one non-zero digit to the left of the decimal, okay? So it's going to look something like this, maybe, 1.23 or 5.67 or something. Something bigger than 1, but smaller than 10, and then it's going to be times 10 to the power of something, okay? Now, that exponent, the times 10 to the power of something, that exponent there is the number of places you had to move the decimal in order to write it in this notation. Now again, sometimes this is expressed as like, you're moving the decimal like it's some magic thing, but keep in mind, all that really means you are doing is multiplying or dividing the number by 10, right? For example, if I have 1.000 and I move the decimal, right? Move the decimal there, I now have 10.000, which is 10 times larger, right? We went from 1 to 10. If I move the decimal again, I get 100.00. Well, that's 10 times bigger again, right? So yes, we say moving the decimal, but keep in mind that moving the decimal really means a multiplication by 10 or a division by 10. For the division by 10, we can think about going the other way, right? Moving the decimal the other direction. So if I take the decimal from here to here, right, I go from 100 to 10. Well, that's 10 times smaller. In other words, division by 10, right? To take the decimal from there to there. Or to take it from there to there, I go from 10 to 1, a division by 10. So moving the decimal is all about multiplying or dividing by tens. And so if the raw answer on our calculator is smaller than 1, we have a small number, right? For example, 0.0123. Remember, we want to write it so that there's one non-zero digit to the left. So we're going to try to turn this into something like 1.23 instead of 0.0123. And then in order to do that, what would we need to do? Well, we would need to take 1.23 and divide it by 10 twice, right? If I take 1.23 and divide it by 10 twice, it's the same as 0.0123, right? I'd have 0.123, then 0.0123. So how we show that is we're going to take this, multiply it by 10 to the power of negative 2. So recall that this really means this negative exponent, it just means we're dividing by 10 twice, right? 10 to the negative 2 is the same as 1 over 10 to the positive 2. It's really just our exponent laws, right? So you can see there we're dividing by 10 twice. So 1.23 times 10 to the negative 2 is the same thing as 0.0123, okay? The exponent will be negative for numbers that are smaller than 1 when written in scientific notation, because we're taking this and we're dividing it by 10 twice to give us something like this. Now, if we have a big number, as in bigger than 1, the exponent's positive because we're taking that base number and we really are just multiplying it by 10 to give us the equivalent, raw answer. So 123 written in scientific notation would be 1.23 times 10 to the power of 2. And again, right, it's about moving that decimal. There's in decimal here, right, we're going to move it twice to get to scientific notation. So 1.23 times 10 to the power of 2, because we moved the decimal twice. Okay, now note, this means the same thing. This is saying take 1.23, multiply it by 10 twice. Well, 1.23 times 10 would be 12.3, times 10 again would be, sure enough, 123, right? So it's all about how we move the decimal, and therefore how many times we're multiplying that base number or dividing that base number by 10 in order to give us our original answer, right? So here we moved it twice, and it's a small number, so it's 1.23 times 10 to the negative 2. Here we move the decimal twice, but this is a large number, it's 123. So to move that decimal twice, we multiply by 10 to the power of 2. We'll get some practice with this. Okay, so first up, our raw answer from our calculator. We want to write all of these to 3 significant digits in scientific notation. So here we have, 0.002806. So we're going to need to move that decimal. So here we go, let's count it out. We have to move it to get scientific notation 1, 2, 3, and that will do it because now we're going to have, 2.8 something times 10 to the power of something, right? We can see that will do that. We'll have that one non-zero digit to the left of the decimal. So we're going to have 2.8. Now we need to make a decision here. I'm going to ask you about this, okay? Should I write a 0 or should I make a change there? Right, I'm going to have to make a change. I need to round this 0 up to a 1. I'm rounding it off because I only want 3 significant digits. and the 0 is followed by a 6. So we always just look at the digit directly after the one we're rounding, okay? And since that 0 is followed by a 6, we're going to say 2.81. That 0 gets rounded up to a 1, right? Because 2806 is closer to 281 than it is to 280, right? That 6 is 5 or larger, so we would round up. Okay, 2.81 times 10 to the power of, we know we move the decimal 1, 2, 3 times, so this number is going to involve a 3. We've got to ask ourselves, should it be positive 3 or negative 3 as the exponent? It should be a negative 3, right? Because of the fact that, right? I mean, one way to look at it, this is a small number, right? So we need to be dividing 2.81 by 10 3 times for it to be equivalent to this, right? Not multiplying it by 10 3 times. So 2.81 times 10 to the negative 3. Okay, next one here, 905,036. Well, there's a decimal there, right? I mean, even if it's not written in, you know that you can put the decimal at the end and say 0.0 and it's mathematically equivalent, okay? So we need to move that decimal. This time we need to move it to the left. So 1 time, twice, 3 times, 4 times, 5 times will give me a base number that's between 1 and 10. So I'll have 9.0, and we're about to round off for our third significant digit. I look at 5. It's followed by a 0, so in this case I would round down. I would leave it as a 5. So 9.05 times 10 to the power of, okay, we move the decimal 5 times, and this is a large number, so we're going to leave it as a positive 5, right? Again, what this is saying is take 9.05, multiply it by 10 5 times, and it's the same meaning as this, right? Sure enough, yeah, if I multiplied this by 10 5 times, I'd get 90.5, then 905, then 9,050, etc., until getting us to about 905,000, which is what we wanted to record. Okay, let's do another one here. 3 significant digits for this. We're going to have to move the decimal 1, 2, 3, 4, 5, 6, 7 times. Okay, so we're going to have 1 point. And notice there's no more digits afterwards that we're given, right? That's okay. We can still do 3 significant digits. Okay, we would say this is 1 point, and we just fill in zeros. Those trailing zeros are significant. So we have 1.00, that's 3 significant digits, times 10 to the power of, I forget how many times we moved it. Let's count again really quick. 1, 2, 3, 4, 5, 6, 7 times. So times 10 to the negative or positive? Negative, very good. Times 10 to the negative 7, right? Okay. Finally here, 1,007. There is a decimal here. We got to move it till we have something between 1 and 10. So 1, 2, 3 times to get 1.0. And do I round this up or leave it as 0? I round it up, very good, because it's followed by a 7. So that's 5 or larger. So 1.01 times 10 to the power of, we move the decimal 3 times. This is a number larger than 1, so 1.01 times 10 to the power of 3. Or, 1.01 times 1,000. Makes sense, because that gets us pretty close to this number we were trying to represent. Awesome. All right, so continuing on with our little review here of the basic skills from previous science courses, let's talk about scalars and vectors. What is the difference between those things? So it really comes down to whether or not direction matters. So for a scalar quantity, they have a magnitude. Magnitude is really just a fancy word for a size or an amount. They have an associated number, okay, but that's it. They have a number, it comes with a unit, but that's it, okay? They do not have a direction. So direction makes no difference for a scalar quantity. One way you can think about that is it might mean that you can't cancel it out by doing the same thing in the opposite direction. So for example, energy is a scalar quantity, right? So if you think about this, if you run down some stairs and you're feeling kind of tired, you burned up energy, right? Can you now run back up the stairs and get that energy back that you just used? No, that doesn't make sense, right? If you push something to the left, it uses energy. If you push it to the right, it's just going to use more energy. You're not undoing that. That's kind of a clue that energy is a scalar quantity. We'll talk a little bit about distance in the next section here as well. That's another scalar quantity. It also might just mean that the concept of direction is completely meaningless for that quantity. It just doesn't even make sense, right? Like mass or time, right? You would never say, oh, I have 80 kilograms of mass, and someone would say, well, in which direction is your mass, right? Well, no, it's just the mass. It's a property of the thing. It has an amount. It doesn't have a direction. Or time, right? If I told you, class starts in 10 minutes, you wouldn't say, oh, well, which direction 10 minutes, right? 10 minutes in which direction? Time doesn't have a direction, right? It just doesn't even make sense. It has an amount, right? We know that 10 minutes is a different amount of time than 5 minutes, but there's no direction involved there. Okay, so some examples of scalars that you've seen before and you'll definitely see again: distance, right? Speed, time, mass, energy, or like bank balance, right? Money is a scalar quantity. You don't have money east or money north, you just got money. It has an amount, but no associated direction. Now, for a vector quantity, they have a magnitude and a direction. Direction is very important for a vector. Okay, it does make a difference for a vector quantity. So even if you have the same amount of a vector, if it's in a different direction, it is not the same thing, because a vector is made up of both that magnitude and that direction. The direction is fundamental to describing the vector properly. So there's kind of like a test I sometimes think of, like a way to test if something is a vector, is to ask yourself if you can cancel it out by doing the same thing in the opposite direction. And if so, it's probably a vector, right? So one example is, force, pushing on something. If I push something to the right, and at the same time you're pushing just as hard on it to the left, well, that object isn't going to go anywhere because our two forces are canceling each other out, right? Sure, I'm pushing it, but you're pushing it just as hard in the opposite direction. They cancel each other out. The object doesn't move, right? Or it doesn't accelerate, okay? Compare that to energy. We would both be using up energy as we sit there and push. We are, converting the energy in our muscles into heat and waste energy, okay? But the forces themselves add to zero on that box. Displacement is what we're going to look at in a second here as well, in quite a bit, right? Displacement is all about how far you went and in which direction. So if you walk forward and then backwards just as far, you end up not having moved, right? Those cancel each other out. So displacement, direction matters. You can cancel it out by doing the same thing in the opposite direction. Velocity, which is kind of like the vector version of speed, right? Displacement is like the vector version of distance. We'll take a look at acceleration in the coming lessons, and definitely a lot at forces in the next unit too. So I think the easiest way to wrap our heads around scalars and vectors, like a lot of things in physics, is to kind of jump in and think about it with examples. And the most simple example of a scalar versus a vector is a distance scalar versus a displacement vector. So let's start there. So an important thing to notice right off the bat, okay, any vector, the symbol for a vector, this is displacement, okay, symbol is a D with an arrow above it, okay, displacement is a vector, direction matters, okay, versus distance, distance is a scalar, still a D, but notice no arrow. So that arrow symbol is how we distinguish symbolically between something that's a vector and something that's a scalar. So you'll see on your formula sheet, lots of things have arrows above them in the formula. That denotes that they are a vector. Okay, so for distance, like I said, it is a scalar. Direction is irrelevant. And all distance is talking about is the total path that's been traveled by an object without caring about the direction that was traveled during that travel time, right? So it's really just saying, how many meters did you walk, right? It's like if you've got like a step counter or something, on your phone or on your smartwatch or whatever, it doesn't worry about whether you were walking forwards or backwards or north or south or whatever, right? It just counts up the total number of steps you took, right? How far did you go? Okay, how many steps did you take? How many meters have you traveled, right? Not worried about direction. Displacement, on the other hand, is a vector quantity, and direction is important. It's the difference between your initial and your final position, as well as the direction of that difference between your initial and final position. So what displacement is essentially asking is how many meters are you from where you started and in which direction, okay? So if we take a look here, right, I like this illustration. I think it does a good job of showing the difference between distance and displacement. So if someone were to go for a walk, right, if they started here, maybe they're going down in the river valley and then coming back out of the river valley somewhere else, right? They start here and then they go all of this distance, right? So the whole time their distance traveled just keeps going up and up and up because it doesn't care about which direction you're going. It's just counting out the total, well, distance that you've walked, right? So that would be their total distance traveled. We're completely ignoring direction. We don't really care. Now, displacement, on the other hand, is going to say if they start here and they end up over here, their displacement on their walk is just how far are they from where they started, and notice in which direction. So in purple here, that would be their displacement, just how far they are from where they started and also in this direction, okay, shown by the arrow there. Distance, no direction, just how far. Displacement, how far are they from where they started and in which direction. Okay, question for you that I maybe want you to pause and think about. What does a car odometer measure, and how can you tell? If you're not sure what an odometer is, that's the little thing at the behind the steering wheel kind of that shows how many kilometers have been put on your car, okay? How far you've driven it in your life, in the car's life, I guess. So which does it measure, distance or displacement, and how can you tell? That's right, it measures your distance, not your displacement, right? On that odometer, there is no consideration for the direction, right? For example, if I drive to Edmonton to from Edmonton to Calgary and then back to Edmonton, which means I've gone roughly, but let's call it about 300 kilometers south to go from Edmonton to Calgary, but then 300 kilometers north to get from Calgary back to Edmonton, right? That, if we're measuring displacement, that would add 0 kilometers to the odometer, right? Because 300 kilometers south, but I ended up back where I started. I went 300 kilometers north after that. My final position was the same as my initial position. So if it was measuring displacement, this should put 0 kilometers on the odometer, but we know that it doesn't, right? Instead, it adds 600 kilometers to the odometer, not 0, right? And so that's how we can tell that it must be measuring our total distance, not our displacement. So when dealing with these vectors where direction matters and doing things in opposite directions can cancel each other out, we've come up with a sign convention. It's essentially like a math trick to help us keep track of those directions and make sure things in opposite directions cancel out. And that is, the trick that we use is that anything in an opposite direction needs to have an opposite sign. There's a convention that we've kind of just agreed upon, okay, in order to, keep things as simple as we can. So there's nothing inherently positive about these directions, but typically we'll say things like, up or north are positive, right? And then things like down or south are negative. Once later in the course, we'll start thinking of this too as 90 degrees. We'll start thinking of this as 270 degrees when we go into more 2D stuff later on, okay? And over here on the x-axis, we have things like, directions like right or east, or later on, we might even call this 0 degrees. And all the opposite directions to that, if we're going to define them as positive, they need to be defined as negative. Negative essentially means opposite, right? So what's the opposite of right? Left. So we would make left negative, right? What's the opposite of east? West. So if we're calling east positive, we need to call west negative, okay? And 0 degrees or 180 later in the course. So notice here, it's actually there's nothing actually positive about north. In fact, you could actually call north negative. The important thing is that south gets the opposite sign when you go to add those vectors, because south is the opposite of north. So again, it's totally okay to call north negative as long as you make very sure that you then call south positive, right? You could call down positive, but now you're defining up as negative. That's okay. That's the important thing. Opposite directions need to have opposite signs so that when you add those opposite directions up, they cancel each other out, right? Looking here, if we were going to find the displacement for our trip, we could call south negative, north positive. We'd have negative 300 plus positive 300 to get 0. And that is our displacement, right? From where we started to where we ended up is the same place, so we've displaced ourselves 0 kilometers. Okay. Let's try one out where we're actually, applying this here. So John walks 300 meters east to the video store, then 400 meters west to a friend's house. Calculate both the distance that John walked and his displacement relative to his starting position. Okay, so we've got two things here, right? First, John walked 300 meters east, then he walked 400 meters west. Okay, so to calculate John's distance, are we worried about the east and the west? No, right? We just want to know the total number of meters he walked. So I'm going to go ahead and call this D1, call this D2, and we're looking to find D total. Okay, well, the total distance he walked is just going to be that first distance plus that second distance. We don't need to worry about positives and negatives and all that kind of thing. Now, instead of calling it total, I'm actually going to go ahead and call it dr. That R is for resultant. You're going to see that come up later in the course a lot, so I'm just going to start introducing it now. It means the same thing essentially as total. It's just the more commonly used format for Physics 20. So the resultant distance, total distance he walked, well, he walked 300 meters. I don't need to worry about positives or negatives here because it's distance. It's a scalar, not a vector. And we just want to know the total number of meters he walked, ignoring direction completely. So 300 meters plus 400 meters, he walked a total of 700 meters. Okay, no direction given because there is no direction for a distance. Checking my sig digs, 3 sig digs here, 3 sig digs here, 3 sig digs here. So that's good, right? 3 significant digits in my answer, and 3 is the least number in any of the data that I used. Now for calculating his displacement, different story, right? This is a vector, so we do need to think about that direction. We're now thinking about not just how many meters did he walk, how far is he from where he started, and in which direction, okay? So we're dealing with vectors. Always a good idea to define your what you're calling positive and what you're calling negative, right? Just a quick visual indicator to show the person reading your work, whether they're marking it or just looking at it, what positive and what negative are going to mean to you. So I'm going to call east positive. I'm going to call west negative, and I'm just showing that really quickly with that diagram. Okay, so now we don't have distances here. We actually have displacements, D1, D2. Okay, so displacement 1 is 300 meters east, and displacement 2 is 400 meters to the west. Okay, now I'm going to, when it comes time to add them, I'm going to have to give them opposite directions. So his resultant displacement, dr, the total displacement, now I'm doing the math. I mean, I can't put an east, I can't put a west into the calculator. So to denote opposite directions, I'm going to use opposite signs. That's where our signs come in. So same idea as before, the resultant displacement is just his 2 displacements added together. But now when I go to do D1, that's 300 meters to the east. So I'm going to make it positive 300 meters. Plus now 400 meters to the west, I'm going to say negative 400 meters. And that's making sure that what needs to happen happens, that these are in opposite directions. Direction matters for displacement, so these need to cancel each other out. Giving them opposite signs will allow that to happen mathematically. So now my resultant displacement, just going to move up here where I got a little more room. My resultant displacement, I'm going to get negative 100 meters. Okay. Now that's not quite done yet, right? We're on the right track, but we need to actually do the work of interpreting this sign, right? Because again, the question didn't say anything about positive and negative. There's no such thing as like a inherently positive or negative direction. We're using those signs to, keep track of those opposite directions, but ultimately now we need to interpret what that negative actually means, okay? So tell me, what does that negative mean for us? Right, we said west was negative. We got a negative answer. So that means this 100-meter displacement is to the west. So his resultant displacement will be 100 meters to the west. In other words, he'll be 100 meters west of where he started. Now, I know you might be rolling your eyes and thinking, come on, I could have figured that out without showing any work, without showing any math, blah, blah, blah. Yes, I get it. Like, we could all figure out that if you went 300 east, but then 400 west, you end up 100 west of where you started, right? We all kind of know that, okay? But that's not the point here. The point is getting used to communicating your work in physics, because things are going to get a lot more complicated than this, right? But it's these base underlying skills and conventions that will guide us no matter how complicated the problems get. So we're introducing them now. Later on, we will definitely, need to show all of this work to get an answer, okay? Important to keep to have that solid foundation of what we're doing when we show our work in physics, okay, and how it helps us keep track of what we need. So this is now a complete answer. We've given the direction, okay, we've done the correct number of significant digits, and so we've communicated this resultant displacement effectively. All right, now we left out a very important step that we should always do on any question where we're adding vectors here, okay, but that's because it was coming up next. So that is the idea of drawing a vector addition diagram. Now, these are one of the most important tools in any Physics 20 student's toolkit, okay? These are, especially when things get more complicated. Again, I know for something like this, you might be rolling your eyes a little bit, but I promise later on a vector addition diagram is crucial for solving these problems, okay? So what is a vector addition diagram, or a VAD for short, okay? What it lets us do is illustrate a situation a lot like what we just did here with John's walk to the store and back to his friend's house, okay? Where we need to find a resultant vector. And that resultant vector is the one vector that would achieve the same result as all of the other vectors together, right? To show you what I mean by that, you could walk 300 meters east and then 400 meters west. The result will be that you are 100 meters west of where you started, right? So it's like saying, okay, you could have done both of these things, the same result as if you just walked 100 meters west to begin with, right? In terms of where you ended up. That's what a resultant vector is. It's the one vector that gives us the same result as all of the other ones together. It's the total, essentially, right? The total result of adding all those vectors together. So the rules for drawing a vector addition diagram, what we do is we draw each vector component tip to tail, is what we say. And all that means is that where the last arrow ends, the next arrow begins. So you draw one vector, represent it as an arrow. Wherever you finish that one, you start the next one, and on and on and on until you've added up all of the vectors you need to add. To find the resultant then, we always just draw an arrow from where we started to where we finished. So from the first vector's tail to the final vector's tip, right? From the beginning of the first to the end of the last. And the order you draw them, the order you add them, actually doesn't matter. I'll show you that when we do this here. So we now want to draw a vector addition diagram to represent John's trip. So we just draw the vectors. In this case, our vectors are displacements. We're just going to draw them as arrows, okay? So we need to draw for John, he did two things. So D1 was he walked 300 meters to the east. So I'm just going to draw an arrow to represent, right? I mean, you don't normally need to do this part, but I'm just going to show. That's where John started. First, he walked 300 meters to the east. Then from there, so tip to tail, right, where this one finished, from there, he then walked 400 meters to the west. So it doesn't need to be perfect, but 400 is bigger than 300, right? So we should draw it bigger, okay? Otherwise, we're going to get the wrong result. So from tip to tail, there's the tip of the last one. I'm just going to use a different color so you can see it. From the tip of the last one, we go back to the west about 400 meters. There's his second displacement. And those are the two vectors we had to add, right? So far, we've done this part. We drew arrows for each vector component, tip to tail. We added them all up, check. Now we just need to figure out visually what's the resultant. Well, he started here, right? And he finished here. So we draw our resultant displacement from where we started to where we finished, right? He did all this stuff, but in the end, he went from here to here. So that's what we would call the resultant displacement. And we can see that, yeah, this seems reasonable, right? He ends up west of where he started. Well, we were expecting that, right? About 100 meters west. Yeah, I mean, if this is 300, that looks reasonable for 100, right? Okay, now I claimed that the order we draw them doesn't matter. In other words, if I had first drawn D2 and then D1, I should get the same result. So let me show you that I wasn't lying when I said that. Let's draw John here. What if we had done D2 first and then D1? Do we still get the same resultant? Well, in that case, we'd start here. First, do 400 meters west. Then tip to tail, we're going to add 300 meters to the east, D1. Now 300 is not as big as 400, so I'm drawing it, about 3/4 the size. Okay, and sure enough, when we go to draw our resultant, he started here, or our diagram started there, and we finished it here. So from where we started to where we ended, that is the resultant displacement. That is dr. Aha, ta-da, look at that, right? Compare this resultant displacement to this resultant displacement vector. They're approximately the same, right? I mean, they are the same. If I had actually broken out a ruler and done everything perfectly, you get the same resultant either way, which makes sense, right? We shouldn't get a different result from going 300 meters east, then 400 meters west, versus doing those in the reversed order. Okay, so the order that you actually add the vectors in your diagram shouldn't change the result you get. You should still get the same result. Okay, so a vector addition diagram, or a VAD, should be included in your solution for any question involving, maybe not vectors explicitly, but definitely whenever we're adding vectors. You should have a vector addition diagram. Okay, on a written response question where you're adding vectors, that will be part of the mark, is having a good VAD drawn. Okay, so we can see from this, right, this idea of distance versus displacement, that if changes in direction occurred, distance is always going to be a larger number than displacement, right? Because when you're changing direction, you're now, possibly canceling out, or at least not working towards as efficiently your displacement going up, right? Whereas for distance, it all just gets counted no matter what direction you're going. All right, so I'm going to turn it over to you for a second here, okay? So you'll find these peppered throughout the notes in every lesson. There will always be a section where it says, okay, now before continuing, go do this one from the practice problems, okay? You are free to do more from the practice problems, keeping in mind that you might not have covered everything in that lesson yet, okay? But at this time, I want you to pause the video and go try this one from your practice problems. Okay, so this is from page 9, number 1. I always put the question itself directly into the notes so you don't necessarily have to flip back and forth. Okay, the answer is there. This is what I use in my synchronous classes for students to check in with me. Okay, but pause the video, try this one out. Note that it says you need to draw a proper vector addition diagram as part of your solution. Okay, and if you've tried that one and you're feeling like, you know what, I want a little bit more practice, there are some more from that practice assignment, like for example, number 2 and 3 are also assigned. Those would be good practice now too, okay? Or if you're a student who likes to wait until the end and do all your practice, that's great too. But either way, I want you to stop the lesson now, try this one at the very least out, okay? Before continuing on, checking your answer against this one. So yeah, go ahead. All right, and so to finish up this lesson with a little bit more review here, we're going to review the concepts of speed and velocity as well as uniform motion here, okay? So speed and velocity, much like, kind of like how with distance and displacement, they was kind of the scalar version and the vector version of similar ideas. Same goes for speed and velocity. Speed is a scalar, and therefore it's just the rate at which your distance, another scalar, changes. So we're not considering direction. We're just saying how much did your distance change per unit of time. So whenever we have a rate of change, which is what speed is, we're just saying how much did that thing change by, in this case distance, divided by how much time it took, right? The change in distance per unit of time. For velocity, very similar idea, except velocity is a vector. We need to consider direction, and it's the rate at which your displacement changed. So notice two very similar formulas, but one has the arrows indicating these are vectors. This is the vector velocity and the vector displacement. This is the scalar speed and the scalar distance. So if we take a look on your formula sheet here, it's a good idea whenever you see a new formula, right? Familiarize yourself with where it is on your formula sheet. You'll see up at the very top left here, we have the average. They just give you the velocity version. Of course, you know that if it's, if you're dealing with scalar and you want speed instead of velocity, it's the same things. We just wouldn't use the arrows there. Okay, so just to kind of get a quick visual of the concept here, okay? So you can see in red there, I've set this person's velocity to 2 meters per second, okay? This one doesn't let me do speed, but I'll just keep them in the same direction so that speed and velocity, average speed and average velocity are kind of the same thing. So what does that mean? Well, it means that when I press play here, right, when I allow him to start moving, every second he's going to travel 2 meters, right? His distance or his displacement will change by 2 meters each second. So let's watch that. 2, 3, 4, 5 seconds, right? Again, he's gone 2 meters in 1 second, 4 meters, 6 meters, 8 meters, 10 meters, right? He's just traveling 2 meters each second. That's what it means to have an average speed of 2 meters per second. So to apply these formulas here, right, they've asked us if we found that the total distance traveled by John was 700 meters and his total displacement, or his final displacement, was 100 meters to the west, and then they're telling us that the total trip, it took exactly 900 seconds, so they want us to calculate his average speed and velocity during that trip, right? Well, all we need to know is how much did his distance change by and how long did it take to get the speed? And for velocity, how much does its displacement change by? And how long did it take to get the average velocity, right? So we can calculate both of these because we have the distance and displacement, and we now have the time that it took, which was 900 seconds. So here we go. Speed will be how much his distance changed by divided by how much time it took to get that change in distance. Always a good idea, for these simpler ones, it's not as hard to keep track, but as problems get more complex, good idea to write out a list of all your given variables, okay? That just helps you keep track when you need them, because now we can just say, okay, I have distance, I have time, I want to find speed, go to our formula sheet, and we recognize that formula, hopefully, right? So the speed will be equal to the change in distance divided by the change in time. Showing our work down the page, we can now sub in that the distance is 700 meters. We don't have to worry about directions or signs or anything because this is all scalar, divided by 900 seconds. Put that into our calculator, we're going to get 0.7777 repeating meters per second, right? Our units would be meters divided by seconds, so meters per second. Now, what am I forgetting for my final answer? That's right, I'm forgetting significant digits, right? So this is way too many. I don't know it that precisely. We go back to the question, we go back to our data, and we say, okay, this had 3 significant digits, this had 3 significant digits. So the least number of significant digits is 3, and therefore my answer should only have 3 significant digits. So I'm going to round this off to 0.778 meters per second. That leading 0 is not significant, but the 778 are. And that last 7 got rounded up to an 8 because it was followed by a 7. So there we go. His average speed during this trip was 0.778 meters per second, meaning that on average, every second, he traveled 0.778 meters. So coming over here now to calculate velocity, right? Again, velocity's similar to speed, but it's the rate at which displacement, a vector, changes. So we know that John's displacement over his trip, his final displacement was 100 meters to the west of where he started, but it still took him 900 seconds to do the whole trip. Okay, so now when we go to do our very similar calculation here, we have to remember that our d is displacement, a vector, and therefore we need to think carefully about our signs, right? So 100 meters to the west, I'm just going to be consistent with what we did up here. And I'm going to say, I'm going to define west as negative and east as positive. That's kind of the default unless you clearly label it some other way, okay? So that means I don't have a west button on my calculator, but I can put in that this 100 meters to the west, we're going to represent that as a displacement of negative 100 meters over a time of 900 seconds. And that's going to give me that my velocity is negative 0.11111 meters per second when I calculate that out. Okay, now again, we need to give a direction, right? If directions are given in the question, we need to give a direction in our answer for a vector anyway, right? If our answer is a vector, okay? Well, velocity is a vector. So that negative, right? There's no such thing as like negative direction necessarily. We're using negative to represent west. So I need to now do my sig digs, and I also need to interpret that negative. So I'm going to say that the velocity is 0 point, still 3 significant digits here, 111 meters per second to the, that negative means to the west. Notice something here too. I don't do a negative and a west, right? That would kind of almost be like a double negative. Negative really just means the opposite. So saying west is what I really mean here. That negative was just kind of standing in for what we had defined mathematically as the negative direction. So I drop the negative and I just be more descriptive by saying west. And there we go. That is John's average velocity over time, okay? Over that trip, I should say. Now notice it's slower than his average speed, which actually makes a lot of sense, right? Because his displacement didn't end up changing as much as his total distance because of the fact that he was undoing some of his displacement for a lot of that trip, right? He went all the way over here and all the way back, but as far as displacement is concerned, he really only displaced himself that much. So on average, his displacement wasn't changing as much each second because there was times where he was working against himself, so to speak. Alrighty. And the last little reminder we'll do here from Science 10, before we just do some examples to finish up, okay, is a review of the concept of uniform motion. Uniform meaning unchanging or constant, okay? So this is motion without acceleration. And don't worry, we'll talk a lot about acceleration in the coming lessons, okay? And all the acceleration is, it's the rate at which velocity is changing, right? So if we don't have an acceleration, it means our velocity is not changing. And so think about what that means, right? We know that velocity is how quickly your displacement was changing, right? Velocity has, kind of two components. It has your speed, essentially, right? And a direction, right? The rate of change of your displacement and in which direction. So that means if there's no change in velocity, you need to be traveling at a constant speed and you cannot change direction. Because if either of those things change, then your velocity changed, right? If you got faster or slower, or you changed the direction you were traveling, either way, that's a change in your velocity because direction is important for velocity. So uniform motion is just going straight at a constant speed without changing directions in a straight line, for the entire time. Okay, so I'll introduce you to something here too as well. We would call this physics principle number 0. Now that's not like a special name given to this by physicists or anything. It actually just comes from Alberta Education, and it's on the back of your formula sheet. You will see on the bottom left side of the back page or page 2 of your formula sheet, there are these numbered physics principles. Okay, and so the reason Alberta Education puts these on your formula sheet is that they like to ask you, and I actually like to ask you as well, what physics concept did you actually apply to solve this question, right? Because that's a good thing to ask students and to get students thinking about, because I'll tell you right now, so much of physics is actually just very, very simple ideas applied in a million different ways. All of the new concepts that you're really going to learn are these 10, between Physics 20 and Physics 30, and even most of university physics, okay? You are going to apply them in a million different ways, but we always start with these simple fundamental ideas to guide our thinking. So uniform motion is described as physics principle number 0. It's the case where an object is moving with uniform motion. It's not changing its velocity, and so it's not speeding up, slowing down, or changing direction. And so this equation that we've just reviewed here, this v equals d over t, okay, this equation actually only works for uniform motion. You can probably tell we're not always going to stick to uniform motion in Physics 20, but for today we are, okay? So this equation only makes sense if something is not changing its velocity, right? And I mean, we can kind of see that because we're just calculating the one velocity or the one speed, okay? It also works with average speeds or average velocities. So maybe you're not interested in its exact velocity at a certain moment, but just over the course of the whole trip, what was its speed or velocity? Kind of like actually what we did here with John, because John did change direction, so he can't have had uniform motion. But on average, we can figure out his speed or his velocity, okay? So this equation, this v equals d over t, it only makes sense if velocity is constant and the acceleration is 0 meters per second squared. And to kind of convince you of that, look here, this is how I think of it, right? I've just rearranged the equation. So if we wanted to solve for distance, let's say, how far someone went, okay? So distance was being divided by time, so I multiplied both sides by time to get rid of that. So the distance could be found by taking the speed and multiplying it by time, right? And you can see why now this only makes sense if the speed wasn't changing, hopefully, right? Because if your speed was constantly changing, let's say, you know, how far, we want to figure out how far you went. Well, it needs to be, if we're saying, you know, okay, if you only went 100 kilometers per hour for 2 hours, then yeah, you should go 200 kilometers, right? 100 kilometers each hour times 2 hours, right? But what if your speed was changing? Like, what speed do you put in there? What if sometimes you were faster than 100 and sometimes slower than 100, right? We can't just take 100 and times it by 2 unless we know your average speed over the whole time was 100, right? If you were changing that speed, it doesn't make sense to just multiply it by time to get the distance. So that's why this equation only works if we have uniform motion or if we're only interested in an average speed or velocity. All right, so let's just finish up with some examples. Alice ran 258 meters in 73 seconds, while Bob ran 320 meters in 96 seconds. Who had a greater average speed? Okay, so we can't say Alice didn't go as far, but she also didn't run for as long. Bob went further, but it also took him longer. So to calculate the average speed, we can now figure this out. So I like just as I encounter givens, right? I'm going to call that change in distance for Alice and time for Alice. And then I'll just do the same for Bob there. Sometimes it's nice to just write your givens in directly as you see them. So let's go ahead and calculate Alice's average speed and Bob's average speed, and we can compare to see who was faster. So for Alice, her speed is going to be her distance divided by her time. So Alice's speed is Alice's distance, 258 meters, divided by the time it took her to go that distance, which was 73 seconds. And so we get that Alice's average speed was 3.5342 meters per second. I'm going to save that unrounded answer just for comparison purposes. And honestly, here our final answer is just going to be who was faster. So sig digs aren't as big of a concern here. Our final answer isn't the number itself. Okay, now let's calculate Bob's. Bob traveled 320 meters, and that took him 96 seconds. So we get that Bob's average speed was 3.33333 meters per second. Aha, so always be careful here, right? You want to make sure you've actually answered the question. So I always tell students, once you've, done your calculations, make sure you go back and read the question one more time to make sure you've really covered what it asked you, right? So it didn't just ask us to calculate their speeds, it asked us who had a greater average speed. Well, Alice did, right? Alice covered on average 3.5 meters each second. Bob only 3.3 meters each second. So Alice had a greater average speed than Bob. All right, okay, so that's really our final answer there. To be honest, we probably should do our sig dig rules for these here, but again, we can tell that we've answered the question by even with our unrounded answers here. So we're safe to make sure that that's clear and we're good to go on that one. So moving on to example 2 here, we have a car that moves with an average speed of 45 kilometers per hour. And it does that until it's traveled 65 kilometers. Now we want to know the time that was taken to complete the journey in hours. Okay, that's convenient for us here. So I was gonna, as we noticed here, kilometers per hour in physics, we typically want to work with base units. That's meters, seconds, and once we start doing mass, kilograms. Okay, so kilometers, also a measure of distance, but typically we want to convert those kilometers to meters. Hours, of course, a measure of time, but we would typically want to convert them to seconds. However, in this case, we are okay to not convert because our units are all going to play nicely with each other, right? We have kilometers per hour, and we want our time to be in hours. So we'll do our unit check, of course. We'll make sure that it all works out, okay? But in this case, we're actually going to be okay to not convert units. So to focus ourselves heading into solving this problem, I like to, again, make a little list of the givens, and then also just, what are we looking for? We're looking for how much time went by. So now we can see, okay, I have a V, I have a D, and I want a T. What formula works for that? Well, since this is an average speed and we're dealing with hopefully uniform motion here, okay, we can use V equals D over T. That'll work, right? We want the equation that has all the variables we know, or at least variables we know, but also the one we want to know so that we can find it. Okay, but we want to find time, and currently this equation is not set up with time isolated, right? Speed is the one that's by itself isolated. So that would be quick and easy to put in our numbers if we knew D and T and wanted V. In this case, we're going to have to rearrange or manipulate the equation. But that's okay, we know how to do that, right? So just a little refresher on it, right? Manipulating an equation is all about undoing the things that are happening to the variable you want to find, right? Undoing those operations, okay? So since we are undoing those operations, we're one at a time just going to ask ourselves, what operations are being performed on the variable I want? What is the opposite of that operation? And then you do it to both sides, okay? Now, since we're undoing the operations, we're going to work backwards through the order of operations, right? Reverse order of operations. So instead of bed mass, we're going to do SAM/DEB. So first we're going to undo any subtractions or additions, then any multiplications or divisions, then any exponents, all outside of brackets. Then finally, we can make our way inside of those brackets and we repeat the process, okay? So in this case, what I want to find is time. Now, right now, time is dividing distance. So I'm never going to be able to find time while it's in the denominator here, okay? So first things first, I just need to get it out of the denominator. Now, it's in the denominator because it is dividing distance. Distance is being divided by time. So to undo that, I need to do the opposite of dividing by time to both sides. And the opposite of operation of division is multiplication. So I will multiply both sides by time, right? And I have to do it to both sides because I can't just change one side of the equation and still call it the same unless I've also changed the other side in the exact same way. So by multiplying both sides by time, we see that this just cancels to 1, and I'm left with distance here is equal to, and on this side, speed times time. Okay, we're getting there, right? At least now it's out of the denominator, but is time isolated? Not yet. Okay, so why isn't it isolated? Because it's being multiplied by speed. So we need to undo that with the inverse operation, the opposite operation. So what's the opposite of multiplying by speed? It's dividing by speed. So if I divide both sides by speed, that's going to cancel, and we get that. The time that's gone by will be equal to the change in distance divided by the speed. And hey, we did it. We've isolated time. We're now ready to plug in our numbers and solve for what that time must be. So here we go. Just going to move up here where I've got a bit more room. The time that must have gone by is going to be equal to the distance, so 65 kilometers, divided by the speed, so 45 kilometers per hour. and we get that the time is gonna be 1.44444. Okay, what are my units? I mean, you might be able to reason that it's gonna be hours, and you are correct, but let's do a unit check here. Let's do our unit analysis, right? I've got kilometers being divided by kilometers per hour. Well, kilometers being divided by kilometers, that can just cancel out, and then we're left with 1 over, right? This cancels to 1. Hours is in the denominator, right? Essentially right now, our units would be 1 over hours. Those kilometers canceled to 1, but that's a per hour in our denominator. Well, recall, right? Dividing by a fraction is the same as multiplying by its reciprocal. So this is the same as 1 divided by 1 over h, but that's the same as multiplying it by h over 1. So we have 1 times h over 1, which is just hours, right? H, hours. So definitely feeling good about our answer now. We got the correct unit we thought should come out by doing our unit analysis there. And the last thing to do here is just check for significant digits. And sure enough, this is way too many. I only want to have 2, right? 2 sig digs, 2 sig digs. So the time that we would record is 1.4 hours. Okay, there's our final answer. If we were recording this in, Smarter Marks or on a Scantron sheet, we would always start in the left space. Okay, we do record the decimal for this format, and then 1.4. So we would say 1 in the first box, decimal in the second box, 4 in the third box, and you won't always need all 4 boxes. That's okay. You just leave the last one blank, but you always start in that first box. Okay, last example here for lesson 1. So, Sally has a meeting across town in 20 minutes. The building lies 16 kilometers away. If the speed limit is 50 kilometers per hour, can she legally get to the meeting on time? So it's a bit of a thinker here, right? I want you to maybe pause the video, take a second, and think about how could we answer this question? What would we actually do in terms of a calculation or a check? There's actually more than one valid approach you could take, by the way. So where my head goes with this, what I'm thinking of, right? We're not told her speed necessarily, we're told the speed limit. Okay, so what we could do is calculate the speed she would need to have because we have the distance she has to go and how much time she has to get there. Well, D and T, we can calculate average speed, right? And if we can figure out the speed she would need to go, we can compare it to 50 kilometers per hour and see if she's able to, stay under that speed limit. But there's different approaches you could take. You could use the speed and the distance to calculate the time and then see if it's possible to make it there in 20 minutes using that speed, the legal speed and the distance she has to go, right? Or you could use the legal speed and the time that she has and see if she can make it 16 kilometers in that time. I'm going to go with that first option, but by all means, if your brain went to one of those other options, there's nothing wrong with that at all, right? There's more than one way to approach this. So she needs to travel 16 kilometers and she needs to do it in 20 minutes. Now, I want you to take a look at our units here and think about them, right? Are these units going to work well together? Our speed limit is in kilometers per hour. Our time is in minutes, right? So these numbers are not ready to work nicely with each other, right? We're going to get, if we just did D over T now, we'd get kilometers per minute. There's nothing wrong with that, but we can't compare it directly to kilometers per hour until they're both in the same unit. So in this case here, since I know my speed I'm trying to compare to is kilometers per hour, I'm going to choose to convert this time in minutes to hours. Again, though, you could also convert this to kilometers per minute if you wanted, or you could even convert everything to meters and seconds if you wanted to do that. Okay, but I'm going to choose here to convert these minutes to hours. Let's do a quick refresher on how to convert units. So to convert units, we just need a conversion factor. And really what a conversion factor is it's kind of like a fancy 1, so to speak. And what I mean by that is it's just the ratio where the numerator and the denominator are actually the same thing. They're just expressed in the different units. It's like the exchange rate for one unit to another, in this case for minutes to hours, okay? So a conversion factor is always just a fraction, okay? And what we need to do is we need to multiply by this fraction and end up with the same thing but measured in a different unit. So not the same number, right? But a number representing the same thing measured differently. So I want to say how many hours is 20 minutes, okay? Well, first things first, I need to make sure that in my fraction, minutes are the thing that cancels out, and I want to be left with hours, right? So if I put minutes up here, they're not going to cancel out. I'm going to have minutes times minutes. That gives me minutes squared. Uh-oh, that's even worse, right? I want minutes to cancel out, and I want to be left with hours, right? So you can see here, we're just saying how many hours per minute, okay? Well, there is 1 hour in every 60 minutes, right? It takes 60 minutes to make an hour. So we can see here that this is what I meant when I said it's kind of like a fancy one, right? Because 1 hour is the same thing as 60 minutes. So it's something over itself, just measured differently. And that's important because since we're, in a sense, we're multiplying by 1, we're not changing what this actually represents. We're just changing how it's being measured, right? So we can double check here very carefully. Yep, minutes divided by minutes, those are going to be gone. And sure enough, we'll be left with hours just like we wanted. So we're going to do 20 times 1 over 60, or essentially 20 divided by 60 to find that 20 minutes is 0.33333 hours. Definitely not going to round that too much. This is what I was referring to earlier. Sometimes you need to make a calculation along the way, and then you're going to need to use that number again later. If we kept rounding this over and over and over again, it could end up actually making our final answer off. So I'm going to keep a lot of extra digits there as I go, okay? One last thing I'll say on unit conversions here, okay? Don't be afraid to trust your gut too, right? Like use your common sense. You know that it takes 60 minutes to get just 1 hour, right? So 20 minutes is not even 1 hour. And we confirmed that with our calculation, right? It's not even 1 hour, okay? Sometimes students will accidentally flip this around and, it happens. We all make mistakes. I'll do it a lot, I'm sure, in these videos. You'll catch them, okay? But we can tell that that doesn't make sense because that would give us 1,200, right? 20 times 60. Well, that doesn't make any sense. If it takes 60 minutes to make just 1 hour, how could 20 minutes be 1,200 hours, right? It doesn't make sense. So, trust your gut. Rely on, what you know about these units to help you along the way. It's a free way to check your work. All right, but now we've got our units all converted. We are ready. They're going to play nicely with each other. We've got kilometers and hours. Our speed that we're comparing to is in kilometers per hour. So we can plug into V equals D over T. And D, the change in distance she has to go through, will be 16 kilometers. And she only has 20 minutes, yes, but now we know that's the same as 0.3333 hours. And we get that her speed is going to need to be 48. I know that looks like I rounded, but it's actually kind of what it comes out to basically on the calculator. 48 kilometers per hour. Now, again, always go back and check. Have we actually answered the question, right? We don't want to put a box around that and say we're done because the question wasn't what will her speed need to be? It was, can she legally get to the meeting on time? So, can she? Yes, she can. She only needs to travel at 48 kilometers per hour in order to cover 16 kilometers in 20 minutes. So since the speed she needs to go is less than the speed limit, she should be able to legally get there on time. So there we go. There's our, final answer. Our final answer is just yes, she can legally make it on time. And here's our work justifying that. Okay, so that is it for the notes and the video lesson for lesson 1. Okay, now it's your turn. Okay, so, think of playing a sport, right? If you wanted to get really good at soccer, right, would you just watch someone else doing soccer, right? Would you watch soccer players on YouTube? No, right? You don't want the first time that you actually kick a ball to be during the game. So it's the same idea with learning any skill, right? With physics, yes, watching me do these examples in the notes might be an important part of the learning process, but ultimately the most important piece for your learning is getting that practice. Okay, so now what you should do, maybe take a little break, but you can go do the remaining practice problems for chapter 1, lesson 1. Okay, I've listed them here as well, so they're convenient for you to find there. Okay, and the instructions for how to access it are all there as well. You can check your work against my solutions, or you can see the textbook solutions. To be honest, the textbook solutions are a little neater, but sometimes it's nice to see it the way, that I wrote it during the lesson as well, okay? So go do those practice problems, try them out. If there's any you're getting, having some trouble with, that's okay. Try it a couple times and then make sure you're always reaching out to me for help as needed, right? Book a meeting, send me an email, whatever, okay? It's okay to get stuck. We all get stuck. But then you want to make sure you're taking the steps to get yourself, back on the right track and get things figured out so you can go to the next lesson feeling confident to take it to the next level. All right.